So as an application of the separation of variables, the SIR model is the one that we usually study first, not only as an application of the separation of variables, but also because it's a historical model, one of the easiest ones, and one of the models that come to mind even if you are outside math biology, so to speak, because it's as simple as possible. I won't want to say easy because there are still some issues with it that are not that obvious, but in terms of the amount of clutter or terms that you can put into it, it's really as minimum as it gets, and still captures pretty much a typical feature of an epidemic, in which you don't have only an infection process, susceptible infected, but you also have some recovery. But many other features, of course, are not in the model. You can add them to make it more realistic depending on the disease parameters or features. Those are variations of some of those will be in the homework as well. So at the very least, we have an infection process that assumes the population is well mixed, right? The mass action low for the infection from susceptible to infected, and recovery from infected to recovered. And notice that this model assumes no disease mortality. It assumes full immunity, because people who are recovered don't become infected again. Now, of course, this may be realistic just for a specific time frame, right? I mean, during the epidemic, and then if the immunity is only lost after a year, of course, you run the model one more time next year and so on. So obviously, these constants are positive, the recovery and the infection rate. And remember our discussion previously with the meaning of the removal rate. So take a moment so we can pause the video and ask yourself, how would you say in your own words, what is the meaning of 1 over r? So remember, the reciprocal of the removal rate from any equation estimates the time spent in that category. Recovery indicates leaving the infected class. So 1 over r, recovery is the removal rate from the infected class. 1 over r is the time spent in I class. Or in a more natural way of speaking, 1 over r is the duration of the disease, the time you are infectious or infected. And that's going to be important, obviously, when we reproduce or we compute the epidemic reproductive number, as you'll see later. So as it turns out, this is one of the rare cases in which we could actually do some integration in the model. Most of the time we cannot do that. But before we do this, let's try to see how much we can gain from understanding the evolution of the disease or the model without actually solving for it. So let me state one thing which is quite important, and which we can gather this in an intuitive fashion. We don't need a formal proof for it. No matter what happens, no matter the size of lambda or r, so we can intuitively notice that how fast the epidemic progresses depends on the relative size, the absolute size of r and lambda, but also the relative size between them, between the infection rate and the recovery rate. For example, a huge recovery rate may exhaust the epidemic very quickly, because the recovery happens so fast, it doesn't allow enough time for I of t to increase and cause lots of infection. And the opposite can happen, of course, if lambda is really big and r is small. But no matter what the size of lambda and r, we should point out that eventually I of t goes to 0 as t goes to infinity. No matter what, I of t goes to 0. One way to gather this intuitively is to notice that the population, so notice total population is constant. No individual comes from the outside in the population, no individual dies, and mathematically we can see this by adding the equations, the derivatives. So therefore, s plus I plus r is constant. So all we have is basically transfer from these classes. You have basically three categories of individuals. There is some transfer from S to I, some transfer from I to R, but eventually, like I said, I of t goes to 0. So the main question is, for example, when the game is over, when the epidemic is over, what is the final size of S and R? This is the only measure we're going to have to analyze basically the epidemic if we can find this answer. The final size of S or R, each of them can tell me how many people were infected eventually in this epidemic. All infected will be recovered eventually. So the number of recovered is the number of infected. I can also gather the same information by looking at the difference from the total population in the S class, right? I mean, knowing the initial value of S and the final size, the difference between the two will be the number of people who are infected. Why does I of t go to 0 no matter what? I mean, mathematically, we can get this. I mean, so there is a way to understand this mathematically. So for example, if it wasn't the case that I of t goes to 0, if I of t always remains positive, no matter what, strictly positive, so let's say it's always greater than some positive constant, basically you would say that R prime is always greater than some constant, strictly positive constant. Which means that would mean R of t goes to infinity exponentially. Like if you were to integrate this, that means you have an indefinite growth of R. And we know that's not possible because we have a total population constant. So at some point, all of these categories, S, I, and R, will have to not go beyond the total population size. That's not possible. Intuitively, you can tell that I of t goes to 0 because as S depletes, right, because of the infection, eventually this term is going to be lower and lower. It's going to be lower either because S goes smaller, which is going to happen. S can only go down, right? I mean, the susceptible class can only decrease. And on the other hand, the removal rate is constant. So the removal rate, the recovery rate is the same no matter what the source. So eventually, of course, the difference of these will be negative. And then I prime will be essentially below a negative exponential, which means it will decline to 0. So the main question then in terms of predicting the epidemic is whether you have, what do we mean by do we have an epidemic or not? What public officials want to know essentially once the cases start to appear is whether you have a spike first and then a decline. So the evolution for I of t, essentially based on our intuitive analysis so far, is that either it's going to be a decline to 0 from the beginning. So you have basically some initial number of cases dropped in the population, but then they dissipate. That's not to say you won't have new infections, but it will be on a declining slope. So the number of infections is going to decline as t goes on. There's not going to be any spike. On the other hand, what can happen, which does happen, right, when you have serious epidemics, is that for a while, you're going to have an increase in the number of cases and then a decline. So these are the two possible outcomes. And of course, this second feature is what public officials are more concerned. The whole, by now, most people who watch the news with the coronavirus epidemic, by now, most people learn the concept of flattening the curve. Right, so I mean, the whole idea is that since we know already we're going to have a spike, that's obvious from the number of new cases. The question is how big the spike is, because the worry is that if you get to a point in which the number of infected people overwhelms the hospital capacity, then you're going to have the problem of turning away sick people from the hospital. So that was the only or the main excuse for the lockdown and all of those measures in order to flatten the curve. Okay, so I mean, the whole goal is not to prevent an epidemic, but the goal is to do something so that the spike doesn't go up. Although that may entail, of course, as you can see, a longer duration of the epidemic. Because flattening of the spike automatically means lengthening the time range unless something else happens. So if the only thing that you achieve is just flattening the curve. So how do we tell mathematically actually if we have a spike or not? Actually, it turns out this is not that difficult. To tell whether you're going to have a spike first or not, all you got to do is to look at the equation for I and look at the overall sign of the derivative and imagine what happens at the beginning of the epidemic. So let's say I start the epidemic with some 2 individuals infected in an otherwise healthy population. So let's say we have 100 susceptibles. You drop 2 extra infected, and no recovered initially. So that means we have 102 people. And there will be 102 people from the beginning to an end. Well, it's all about the sign of this, right? So initially, the sign of I prime is given by lambda S naught minus R. Oops, it's out of range, sorry about that. So the sign of I prime is given by lambda S naught minus R. If lambda S naught minus R is greater than 0, then we have a spike in I of t before I of t approaching 0. So this is the key element here that will basically allows us to estimate whether we have an epidemic or not. Now remember, we always should strive to give that a biological meaning in terms of the capacity of a typical infectious person to spread a disease. And this ties up to the reciprocal of the removal rate that we talked about before. So let's do that on the second page. That quantity, lambda S naught minus R greater than 0, can be rewritten as lambda S naught over R greater than 1. So we can give an interpretation if we look individually at these 2 factors. So this 1 over R is the duration of the disease. And lambda S naught is the number of new infections per unit of time caused by 1 infected in a susceptible population. This is kind of a mouthful, but try to get used to this concept. And you can use different words, but more or less that's what you want to mean when you describe the meaning of that lambda S naught. So this quantity, which again is called the epidemic reproductive number, or the basic reproductive number, or just the reproductive number in the context of a disease, it's always interpreted from the point of view of an infectious individual. So, or from the point of view of the disease, if you want, because it's a way to indicate how much the disease reproduces itself in a healthy population. So the meaning of that term that is compared to 1 is to say we have a typical infectious individual, patient 0 if you want, right? But we imagine otherwise a nearly susceptible population. Nearly everybody is susceptible in the beginning. And so this is the infection rate. So from the point of view of just 1 infectious individual, this quantity is how many new infections happen per unit of time. That's the meaning in the model, right? Remember, in the model we have lambda Si. So this is basically coming from that. So if I is 1 and the population is otherwise susceptible, like it happens in the beginning, then the meaning of this quantity is per unit of time, that's how many new infections that individual produces. Per unit of time is the key word here, because this is why when you multiply by the duration of the disease, then you can estimate how many infections 1 infectious individual can produce during his infectious status. I mean, during the time while he or she is infected. Excuse me. So you multiply the unit of time with the whole duration of the disease. So when that's said and done, the product of the two signifies the number of new infections that one infectious individual will cause while he or she is infected. So during the time that person is infected. And that's the reason why we do this rearrangement to compare it to one, because it's very intuitive. If during, let's say the disease takes 7 days. So if a typical infectious person can cause more than one infection during those 7 days, then obviously we have a spike, because the disease will have a net positive reproduction rate. You will cause more than, so that means you will replace more than yourself. You will cause more than one infection. And that's why if the reproductive number is 2, 3, 4, and so on, that signifies a very fast progressing disease, because the number of new infections causes a huge spike. Eventually, no matter how big R naught is, the disease will go away. In fact, it will go away faster, right? I mean, if you had immunity, because eventually most people will be infected. So then you won't have any new susceptible to infect. So that's why eventually still I of t goes to 0. The question is whether there is a spike and how big that is. So in the SIR model, like I said, R naught, with this epidemic reproductive number is typically denoted by R naught, is given by lambda S naught over R. Sometimes you will see people mentioning just lambda over R. This is kind of like a more extreme view, in the sense that if lambda over R is greater than 1, you're going to have an epidemic no matter what. So regardless of S naught. So regardless of whether you have initially enough susceptible or not, even if you have just one susceptible, if lambda over R is greater than 1, you still have a spike in the epidemic. Whereas this one is a little bit more precise, because it gives you a measure of whether you have an epidemic or not, depending on how many susceptible you have. Remember, you need to have susceptibles mingling around the population for the infection to occur. If there are not that many susceptible to begin with, then you won't have a spike under the assumptions of this model. So with that in mind, let's close this part, and then we're gonna talk about in the next part on how to find the final size of the epidemic, how to integrate the model, and discuss the final size of S and R.